Please sign into that list. I already got one name from Keyway. The other ones who have not given me names or titles, please fill in that list. Can you pass that around, please? Second, today we are now coming to the method of balanced truncation. And this actually relates model reduction to matrix equations, as you can already guess, because in the part where we talked about balanced realizations, the gradients showed up, and we showed that the gradients, they solve Lyapunov matrix equations. And we'll see that you can do balancing not only with the controllability and the reachability gradient, but also with other positive semi-definite matrices or positive definite matrices that are related to the system, and that leads to solving then also algebraic Riccati equation, which is the second type of matrix equations we will discuss. Today we will introduce the method of balanced truncation. I will give you the method in a nutshell. Then we will go back a step and go through two motivations for balanced truncation. I think it's some nice mathematics behind, and I thought that it would be good to learn about these things. And then we'll discuss some variations of the method at the end. So in a nutshell, we just remember that for a stable system, which we assume throughout at least the first half of this section, realized by A, B, C, and D. Again, now I leave out the E matrix. The method has been extended to descriptor case. That means that to singular E matrices, but the derivations get a lot more involved, and it gets quite technical in contrast to the interpolatory model reduction methods, where it's easier to incorporate the E, but it's doable here as well. And if E is invertible, it's also not a big issue. It's just you put an E here, E transpose here, E here, E here, E transpose here, and solve these equations. And you can do the same stuff. Anyway, let's assume that E is the identity. It makes life easier. We know that P and Q are the controllability or reachability gradient. Q are the observability gradient. They are, under the given assumptions, positive semi-definite matrices by definition. And if the system is minimal, controllable plus observable, they are both invertible. In that case, we know that we can balance the system. That means we can find a state space transformation, change of coordinates in state space, so that P and Q become equal and diagonal. And on the diagonal, you find the Hankel singular values of the system ordered in decreasing order. In the minimal case, also the last one, sigma n, is larger than 0. So, as I said, we have already seen that we can compute a transformation to this coordinate system. We have even shown in the exercises how this transformation looks like. So we can go to these balanced coordinates, and we can do truncation. And that's all. That's the method. So the method is you go to the balanced coordinates, take the principal leading submatrices of A, B, and C, don't change D. That's your reduced order model. So as easy as it is. Point A, the problem that we have to face is solving these Lyapunov equations is quite a challenge. As I said already yesterday, you have n square unknowns if the system of your state space is, if the dimension of your state space is n. So this is a challenging equation to solve. Point B, you don't want to do that explicitly. Yeah? You probably don't want to compute the full T, because that will be a dense matrix. If n is 100,000, you don't want to do that. So we have to find ways to avoid solving for P and Q, or to somehow find a way to make it efficient to solve these equations or get the information that we need. And point B, we need to avoid explicitly solving this transformation. And that's the topic of the next. So we just to remind you, we proved already that Hankel singular values are system invariants. They don't change under this transformation. And for the spectrum of the product P times Q, of which the square roots are actually the Hankel singular values, that doesn't change under this contra-gradient transformation that diagonalizes P and Q. That calculation we have done already. So the way to implement this is usually the SR method. We will have an alternative in the exercises, the balancing free SR method, where you avoid going explicitly to the balanced coordinates. SR here stands for the SR that shows up in this singular value decomposition. As you remember, this balancing transformation was based on information that you obtained from this singular value decomposition. You used S, U, and V, and sigma, and that defines T as well as T inverse. You can explicitly write down T and T inverse in terms of the quantities that arise here in this transformation. So what you need are the Cholesky factors of P and Q, or any other factor that gives you this form of P and Q. It doesn't need to be a Cholesky factor. It can be so anything else that gives you P and Q. And this is also already the basic idea to make it implementable for large-scale problems. You don't compute P or Q at the beginning. You directly try to find an S and an R that approximately gives you P and Q if multiplied with its transpose. So the algorithms that we will develop for solving Lyapunov equations, for computing the gradients, they will essentially not give you P and Q explicitly. They will only give you S and R. And usually not the Cholesky factors, but something else. So anyway, if you have S and R, you can compute this SVD, and then you just define W and V so that you get exactly, let's just go back, so that you exactly only compute A, 1, 1, B1, C1. So in that setting, what we need to get these upper parts of A, B, C, and D are the first R rows of T and the first R columns of T inverse. And we have this explicit formula for T and T inverse based on the SVD, so we just can pick out those rows. And that's what's done here on this slide. So you pick out just the first R singular values of this SVD, singular vectors, right? Singular vectors, and the Hankel singular values that remain in the reduced order system are in sigma 1. And yeah, and the same you do for V. And these give you, first of all, it's clear, they give you a projector. That's just clear from the properties of the SVD, like we had it in the exercise already seen in a way. It's an oblique projector, obviously. So balanced truncation can be interpreted as a Petrov-Galerkin projection method. And I forgot to write down now, of course, the reduced order model is, as always, this thing here. And d hat is not changed. So that's the usual thing. And there are some nice properties that we will partially show. In any case, it's clear that a reduced order model is stable with Hankel singular value sigma 1 through sigma r. This is just a consequence of the fact, well, I have it on the slides anyway later on, that in these balanced coordinates, the solution of the Lyapunov equations become diagonal, and then you will see that the Lyapunov equation for which you have to, well, the Lyapunov equation which describes your reduced order gradients are just A11, sigma 1, and so on, plus sigma 1, A11 transpose. Sigma 1 is obviously positive definite, and Lyapunov stability theory will then tell you that A11 must be stable. And of course, because the reduced gradients are just both equal to sigma 1, the Hankel singular values of the reduced order system are just sigma 1 through sigma r. And then what you get is this error bound, which is quite, well, it's not so easy to prove without a lot of information. Either you have to assume many things known to be from system theory, which you will not have, or it's a quite long proof. The original paper was 80 pages, more or less. Of course, it has been condensed, and in textbooks now you can find it on 4 or 5 pages. But usually you have some preparatory work done in the textbooks so that you can write it down in shorter time. So what this tells you is that the approximation of the transfer function in the H-finity norm is bounded from above by this quantity, which is twice the sum of the tail of the Hankel singular values. So all the Hankel singular values that you throw away are summed up, and then you have this factor of 2. It can be sharpened a little bit if you have, say, double or triple Hankel singular values. Then only one of the copies has to go into the sum. This is particularly interesting for some problems for which sigma 1 has a high multiplicity. And these examples exist. It's like filters, for low-pass filters, high-pass filters. They have usually a constant number of sigma 1s, a high number of sigma 1s, say 20. If you, in MATLAB, you can invoke the command Butterworth that gives you the state space representation of the Butterworth filter. It has basically the transfer function looking like this. So signals in that range don't get transported to the output. Here you get the signals can just pass through, and here on the frequency range nothing comes through again. That's not so easy to approximate. You'll have all the sorts of things that you know from Fourier analysis, if you know it, a Gibbs phenomenon, and so on. In any case, say you have 20 of these sigma 1s equal, then well, it doesn't help in this bound, but it tells you that you probably have to, your reduced order model has to include all of them. Otherwise, your error bound will not give you anything. It will give you 100% error. And also the approximation will be poor. If you have multiple of the small eigenvalues, as I said, you only count them one. This makes the bound a little bit sharper. And I give you just a sketch of the proof. And just so assume that is our Gramian in balanced coordinates. Then the bound is in the H infinity norm twice the sum, I called it k equal let's call it r tilde plus 1 to L sigma k. So r tilde is now the Hankel singular, that's N2. It's now the Hankel singular value, the last one that you keep. So the reduced order model would be R equal to N1 plus N2 plus NR tilde. Yeah. It's a little technical to write it down in this way, but for the proof you need that, because you cannot cut in a block of equal Hankel singular values. Numerically, that's usually not a problem, because numerically, if you do it on a computer, you'll never have equal Hankel singular values. So it's not so much an issue. But for the theory, for proving the theorem, it's necessary. So there's two steps of the proof. The first part is let G1 or no, GL equal be reduced order model from BT with sigma L discarded. So you cut here. Yeah? You keep everything but the last Hankel singular value and the associated block. And then you can prove that G minus GL in the H infinity norm is less than or equal to 2 times sigma L. So that's the long part of the proof. And then the short part is obvious. Now you have that, you only use the triangle inequality sufficiently often to get the full bound. And so on. And you apply triangle inequality. So this is always, you take the next reduced order model by truncating the next block until you reach G hat of that size. How do I call that next to last block? That's of course a 0. There's Because in the G hat I have to use some number. GR tilde plus 1, right? And due to the lemma, or due to this result here, we obtain twice sigma L plus and so on plus 2 times sigma tilde. Thank you. All right. So that's the error bound. You can find the proof in Antulas's book. It requires you to read the whole book until that point. There are also, and it's only coming on page 400 or something like that. There are also control theory books that you can find it in a direct way. There's a book of Green and Limebeer in 1995 and Zhu, Doyle, Glover. It's not so easy, it's technical, but it doesn't lead you through all of system theory to just prove this result. And the original bound is due to Enz in 1984. Question? So this is, of course, was the breakthrough for the method of balanced truncation at that point. When the engineers knew you can exactly say what the error is, at least bound it from above, you are quite happy. So you can have an adaptive method. Once you have all your Hankel singular values computed, you have a tolerance given for your reduced order model. Say you want to have 10% or 1%. You just make that bound divided by the H infinity norm of your system. If your system is small enough that you can compute all Hankel singular values, you can also compute its H infinity norm. And you make that bound smaller than the tolerance, you have a relative error less than 1%. Well, if your tolerance is 0.01. And then the algorithm can choose the size of the reduced order model adaptively. You don't have to choose a priori. That's a big advantage. Guaranteed stability is another advantage. One of the disadvantages is, first of all, that the computation is quite involved, and that's why after having the breakthrough in control theory, where you had to deal with systems of order 10 that you wanted to reduce to order 4 in the 80s usually, or systems of order 20 that you would reduce to order 5 in order to be able to design a hardware controller, it wasn't carried through to really large-scale problems like coming from finite element analysis, because people didn't know how to solve the Lyapunov equations in that case. And that's changed only with the turn of the century, or the turn of the millennium. Around 2000, the algorithms started to evolve that could deal with this large-scale, in large-scale problems. But this is a good thing. There's also another thing that you may want to note down. I don't put it on the slide. You have also a lower bound. And that's the last Hankel singular value that you kept in your system. Okay. There's another issue with balanced truncation that's more intricate. In cases where, in that lemma here, where this block NL is even, you also know where the maximum of the error is taken. You know the frequency where it's taken. It's taken at 0. And that's bad for the cases that I discussed so far, because you also often want to have good error, a small error, or 0 error at 0. But the theory of balanced truncation tells you that in some cases, at least in some cases, that's where the maximum error is taken. So that's a disadvantage, a further disadvantage that can be dealt with, like in modal truncation, using sort of a Guyana reduction kind of approach. We'll come to that later. All right, that was balanced truncation in a nutshell, and now I want to guide you through a little bit of the theoretical background that motivates balanced truncation apart from the error bound and the system preservation. So for this derivation, d doesn't play a role, so we set it to 0, and we also set the initial state to 0. And what we then know is that by the variation of constants formula, you can relate the inputs to the outputs also in state space or in time domain. Not only, we have done it in frequency domain, and that's where the transfer function came up, but I want to now give you some background where this concept of the Hankel singular value approximation comes from, and why it is basically nothing else as the singular value decomposition in approximating a matrix. And for that, we just first look at this operator here. It maps L2 functions in time domain, now defined on the whole real line, to L2 functions that also have to be defined on the whole real line. And y of t is by the variation of constants formula, because we set x0 to 0, just this integral, a value with upper bound t. That's the first thing that you probably have learned in your ODE course. All right, so the idea would be to approximate that operator. Like in the frequency domain, we have approximated the transfer function. The question was, we cannot solve this H infinity approximation problem there. Maybe we can do something here in time domain. All right. That operator S is not a very nice guy. In particular, it doesn't have an important property that you want to have if you want to define singular values for infinite objects, for operators in function space. It's not compact. So that operator is not good for our purposes. So you also have, in order to see the analogy to the SVD as approximation tool for matrices, you have to see the analogy between linear operator and matrix. Matrix seen as a linear operator mapping from Rm to Rn, right? That's when I taught linear algebra, undergraduate course in linear algebra, that's usually one of the first obstacles in a course for mathematics students, to understand the concept that the matrix is an operator. I assume you have mastered this obstacle a long time ago. Okay, so that's what I already said. We want to do the same thing as for the matrix for that operator. We can't do it because this operator doesn't have an SVD, or at least not a discrete SVD. If you have a continuous part of the the singular spectrum, that doesn't work for approximations. You wouldn't know what to take from this continuous part. So what next thing one could think of, let's assume you have a dedicated time t. In our case, we choose because it's an autonomous system, you can choose t equal to 0. And assume you have reached a certain state at 0. The question that you ask is, what is the kind of energy that I have used to get there? And now if I let the system go, what is the energy in the system after time t? And this is basically the question that this Hankel operator answers. It maps past inputs, so everything that you put into the system since the origin of times, of all times, minus infinity, to now. And then you let the system go, and these are the future outputs, y plus. And that operator looks like this. Looks like it's not here. So there's something wrong here. I think that must be a t up here as well. But then it's not true. Oh no, u becomes 0. So no, it's okay. That's the operator. That's true. Yeah. So this is called the Hankel operator, and then now you can show that H is actually compact. So it has a discrete SVD, and it has singular values sigma 1 through sigma j, and that's what I want to prove now. That these are our Hankel singular values that we have defined as the square roots of the eigenvalues of the product of the controllability region. And just to motivate, well, we have seen the motivation already. Here are the Hankel singular values of a dynamical system associated to a storm model. So it's a weather forecast model. And you see that, again, as we have seen, they drop as is pretty fast. This is, again, the red line is machine precision. So doing a SVD type approximation based off them makes a lot of sense. As I already mentioned, the best approximation problem in the H infinity norm that would be the approximation problem that we had considered in frequency domain. That leads to the, in state space, that leads to this Adamiev-Arov-Krein theory that I already mentioned. So you can do basically the same thing as you do for the SVD, but it's not computationally feasible for large-scale systems. And it leads to this procedure that I called Hankel norm approximation. And it gives you in that Hankel norm, which is then like the spectral norm of a matrix, it's just the Hankel norm of the operator is just sigma 1. It gives you the best approximation in that, as what I said, was a semi-norm if D is present. But it's not so easy to compute. So what I want to do for the rest of the first part of the lecture today is to prove that theorem. And for that I need first some space. You probably have that theorem in the notes, so I can turn off the screen. You don't need to really copy the proof if you don't like to, because in the electronic version of my slides that I will make available via the web page tomorrow, the proof is contained. So It's up to you whether you want to follow or you want to copy. So the Hankel operator was defined by y plus of t is the application of h to u minus of t, and was the integral from minus infinity to 0 of c times a ea t minus tau b u of tau d tau. So the first thing we do, we pull out everything that doesn't depend on the integral of the integration variable tau to the left. Okay. So you see already in the very beginning the structure of the integral formula of the gradients evolving. That's where we are after. What we want to show is that, we want to show that the singular values of h are the singular values of p times q. 0 to the minus a tau b u of tau d tau. Okay, so that's a constant. That's an integral that you can compute, and we call that integral z. Or we call that value that you compute there, or that vector that you compute there, z. Gives us a nice compact form. Okay, what do we want to prove? We want to prove something about the singular values of h. How are the singular values of h defined? It's the same way for operators in Hilbert space as you do it for matrices. The singular values of h are the eigenvalues of h square h, or the square roots of the eigenvalues of h square h. Now we need to know what's h star. What's the adjoint operator of h? I don't want to prove what that is, but I will only write it down. So the adjoint of h is obviously an operator that has the domain as the part of the image of the operator h. So it works on these functions that are L2 functions from 0 to infinity. So we need to know what that is. And taking the adjoint of such an operator means reversing time and taking the adjoint of the kernel of the integral. So reversing time means integral 0 to infinity, because we are working on this y plus functions. B transpose, EA transpose, reversing time, tau minus t, C transpose, and then you apply now to y plus, so that comes here. Okay, that's the adjoint operator. And again, we can pull out what's not related to the integration constant. That's now minus t. integral 0 to infinity e to the a transpose tau c transpose y plus of tau. Okay, let's see if I have the signs right. Yeah. Oops. And now we are ready to calculate eigenvalues of the operator h star h. So this is just h star applied to y plus. That's what we just computed up there. It's the same thing that I just wrote because this is just y plus. It's just this thing here. Yeah. Where now for y plus we can insert hu minus of t, right? So you can insert this here. So what we get is b transpose e to the minus a transpose t times that integral e to the a transpose tau c transpose c e to the a t set theta. Okay, now you get an idea where we are going. We can pull out the set to the right, and let me just do that by wiping. And what you have here, that's of course our observability gradient. So we are heading in the right direction. We have related already our eigenvalues, or at least we have related this operator h star h to the observability gradient. So we have what we get out here is b transpose e to the minus a transpose t q set. All right. In order to compute an eigenvalue and an eigenvector, we need that this left-hand side, so an eigenvector in the setting of function is of course an eigenfunction. It's any of these u minus functions that satisfies this relation. So you need to have, to satisfy this relation, to have an eigenvector and an eigenvalue, and that means that this eigenvector u minus t, or this eigenfunction, must satisfy u minus of t equal to 1 over sigma square b transpose e to the minus a transpose t q set. So now we remember what set was. How it started. So we have, we now need to come back to this here and remember the formula for Z. So we write it down again. First, minus infinity to 0, e to the minus a e to the minus a tau, b u minus of tau d tau. And now we insert this expression for the eigenvector into this formula. Let's do it here. Okay, the eigenvector was 1 over sigma squared. Let's pull the 1 over sigma squared to the left. B transpose e to the minus a transpose tau q z d tau. Okay, and we are almost done. So we can pull out the qz to the left, to the right. That's 1 over sigma squared, integral from minus infinity to 0, e to the minus a tau bb transpose e to the minus a transpose tau d tau qz. And with this little trick that I showed you, or with substitution of the minus tau by s, the integral signs flip, and you get exactly that this is p. This is the reachability gradient. Hence, sigma pqz is equal to sigma square z. So what we have shown is if we have an eigenfunction u minus corresponding to an eigenvalue sigma square of the compact of the operator h star h, then this is, and these are this is an equivalence relation, then this holds if and only if z is an eigenvector of the product p times q corresponding to the eigenvalue sigma square. That shows that the eigenvalues of h star h are equal to the eigenvalues of p times q. And that shows that the Hankel singular values, as we define them as the square roots of these eigenvalues, are the singular values of h. It also shows you a little more. It shows you that the Hankel operator only has at most n finite eigenvalues. Or in particular, it has exactly n hat finite not eigenvalues, finite singular values. N hat was the Macmillan degree of the system. So we have a compact operator with only a finite number of finite singular values. So this is even an operator that satisfies stronger conditions in functional analysis. It's a nuclear operator. It's of trace class. Whatever you want to define, the Hankel operator is in that class. Okay, I think with that proof you deserve the break. Yeah. In a linear system. And here again we go from past inputs to future outputs. I already told you that the Hankel operator is the operator that describes this transfer. And we define the input energy. Input energy, which gets an EC for controllability, because it describes actually the controllability of this state x0. How much energy, or the reachability, one should better say, I guess. One describes the energy one needs to reach the state x0. That's the infimum over all L2 functions in time domain from -infinity to 0 with initial condition for our linear differential equation at -infinity 0. So you start from 0 initial condition at -infinity, and you want to get to x0 at time 0. And the question is how much energy is needed to do that. And that's then the integral, of course, over the time interval. And energies are usually the squared. This is this Euclidean norm of the vector u2 here, squared. So you take in every t, you take that vector as a constant vector, take the inner product, the usually Euclidean inner product, and square it, and then you integrate over the function that you obtain. So this is the input energy, and in the same way you can define the output energy. And it's a little easier. It's just defined as you take your output function obtained by starting at x0 and applying 0 input and square it, and this again Euclidean norm of that vector. All right, so that's the output energy. It tells you how much energy will be in that system over all times once the system is released from x0. Maybe just as a remark, the notation for function x of t x0 u here means it's the solution to x dot ax plus bu of t x of t0. So you start integrating at 0 with initial condition x0, and you apply the function u, and here we have applied the function 0. Now, what you can show is that this is nothing but x0 transpose p plus x0. P plus is the Moore-Penrose inverse of the controllability Kramian or reachability Kramian. In the case that you have a controllable system, that's of course the inverse. Otherwise, it's the Moore-Penrose inverse. And that can be shown to be just x naught transpose qx. And q is the observability Gramian. The proof is not so difficult, but I don't want to do it, I think, because I want to get through with the chapter on balanced truncation today. First you can yeah. Anyway, it's basic idea is you make an ansatz for u of t. You show that for that u of t you obtain that formula. So you make obviously the ansatz u of t so that this integral becomes again this Gramian. That's similar as we did in the Hanker, just in that proof. You make an ansatz like b transpose e to the a minus b transpose e to the a transpose minus something times x0 or something like that. You plug that in here, then you show that you get that formula, and then you have to prove that this is really gives you that particular choice of u gives you the infimum, and that you do by a variational argument. That's the structure of the proof. It takes a while to do it. And this is, yeah, here you just plug in the formula for y. And then you can relate it to the observability Gramian easily, as we have done a couple of times already, just using the variation of constants formula. Okay, now this tells you the following. How to write it down? So if x0 minimizes x transpose px, so if we look at all x0 that minimize that quadratic form, then it is either in the kernel of P, that means it's not reachable at all, or it maximizes this form. For all x0 in the range of P. And that means x0 is hard to reach if x0 transpose px0 is small. Yeah? Let that sink in for a second. If you minimize that quadratic form, that means you maximize the energy that you need to reach it. That makes that state very, very, very hard to reach. So it's a state that in a practical situation you will probably never encounter. And because it needs a lot of effort to get the system there. Effort that you will not spend, and unless it's really the target of your computation, you will never get there. So in your reduced order model, you delete that state. That's one of the motivations. So anything for which that is small we can remove from our model. And this is part of the motivation that I'm trying to explain. And of course, a state for which this quantity is small is hard to observe. Yeah, if it would be 0, it would not be observable at all. If it's small, it's hard to observe. Now the key idea of a reduction process would be to eliminate all states that are hard to reach and hard to observe, but that might be different states or different things. So a state might be hard to observe, but it might be easy to reach it. Yeah, it's not. Yeah. So these are. You cannot automatically eliminate a state just because it's hard to observe, because it might be easy to reach, and so it will be present in your dynamics, probably. So the key observation now is, in balanced coordinates, states that are hard to reach are also hard to observe, because in balanced coordinates P and Q become equal. Yeah. So making that small means making that small. So hard to observe becomes equal to hard to reach. So states that are hard to reach are hard to observe as well. And that means we can eliminate those states now. They will not have anything to do with the dynamics of our system in most cases. And it also tells you that balanced truncation is the method of choice if you're just interested in computing a minimal realization. Yeah, you just apply balanced truncation, and you don't throw away any non-negative Hankel singular values. You throw away all that are 0 and keep all the ones that are positive. Then you have computed a minimal realization. That means we have removed all states from the kernel of P and all states that are unobservable, because that quantity is 0. So this is one way to motivate balanced truncation. I should mention here, maybe if you're interested in nonlinear systems, that this motivation carries through to nonlinear systems. You can define, for nonlinear systems, you can define these quantities in a similar way. There's nothing special about linear systems in this definition. Just you don't get these expressions anymore. You get certain functionals, and then you could, in principle, also do model reduction based on this. That has been done in particularly by Jacqueline Scherpen in the Netherlands. She has advertised this nonlinear model reduction method, but it's not computational. It's really, you can do it by hand for small problems. And I've never seen applying it by anybody for systems larger than order 5 or 7 or something. Because it's really, you cannot, there's no way to do the computations automatically. At least none that I know of so far. What has been done is so-called empirical Gramian methods that sort of compute P matrices and Qs that in the linear case would be approximations to the Gramians and play the role of these energy presentations, and then you can base your model reduction approach on that. And if you look at it from the right angle, what you get is proper orthogonal decomposition in that way, if you have ever heard of that method, or principal component analysis. Okay. Do I want to? Maybe as a last thing to put that into a formula, the energy transfer in sigma is E is equal to EC of x0 divided by EO of x0, vice versa. So the transfer from input to output energy, or the ratio of input to output energy, which is an interesting quantity, by the formulas that we just have computed, that's x dot transpose qx naught divided by x naught transpose p plus x naught, x naught in the range of p. Otherwise the denominator becomes 0. And in balanced coordinates, this is just, and that's a calculation that you can do yourself, 1 over x tilde square times sigma k squared x. So if you apply balancing, you make Q and P equal. Let's assume for simplicity there is an issue here with uncontrollable modes. Then P is invertible, so we can replace it here by the inverse. If you go to balanced coordinates, you can transform x0 also into that new coordinate system, and then you see what you end up with is this expression, and then you see again small Hankel singular values will eliminate all the components that correspond to these states that are hard to reach and are hard to observe. And this also gives you a motivation why the sigma case should play a role in the error bound. So these are two basic observations. The Hankel singular values, or the balanced coordinates together with the Hankel singular values, tell you which states in your state space, which directions in your state space are unimportant because of this energy transfer consideration, and those are the directions you can eliminate because you will not go into this outer space in any practical situation. So you can work with lower dimensional subspace. And the other motivation was that we can see balanced truncation as a procedure like the SVD approximation of a matrix if you apply the SVD approximation to the Hankel operator. So these are two basic things that I hope you memorize from this lecture. And for the rest of the lecture, I will go back to the slides. Okay, we have just, for the break, we proved that theorem. Another theorem is what I already said, is essentially that if the system is computed with a reduced size less than the Macmillan degree, the reduced order model is balanced, stable, minimal, and the Hankel singular values are sigma 1 through sigma r. And just to point to that, I think it's also sort of related to one of the exercises we did already on Monday, on Tuesday. You can see that if you have balanced coordinates and you write down the controllability Lyapunov equation, then you see that the reduced order model has this controllability Lyapunov equation. So sigma 1 is the controllability gradient. In a similar way, the sigma 1 also satisfies the observability Lyapunov equation for the reduced order model. Another thing that you can see from this slide is that also sigma 2 satisfies the Lyapunov equation, namely A22 sigma 2 is equal to sigma 2 A22 transpose plus B2 transpose equal to 0. So A22 is also an invertible matrix because of Lyapunov stability theory. And if we have, if you have proof that, or if you, at least if you started with a minimal system, this is true because in order to apply Lyapunov theory to that lower Lyapunov equation, you need to assume that A22 B2 is controllable, and this will be the case if the original system was minimal. Controllability plus satisfying such an equation with a positive definite sigma, positive definite solution then implies stability, and that's what we had in the exercise. Okay, minimality of course follows from the fact that the two gradients of the reduced order model are positive, so the reduced order system is controllable and observable. So now just a short glimpse at that problem that I briefly touched upon when we talked about the error bound. For some models, the balanced truncation reduced order model will have the maximum error at 0. And even if it's not in that situation, it often has a large error at 0. So you can get rid of that by the static condensation approach that we use for modal truncation. For that, we just consider our balanced system, assume that this is in balanced coordinates, partitioned as before, and we do the same thing. Maybe another way to see it, and that was the way it was introduced in control theory without knowing about the Guyane reduction, that was around for 30 years already or 20 years, was that what you do in balanced truncation, you can interpret it as setting the states x2, which you assume are hard to reach and hard to observe. You set them, or that part of the state vector, you set that to 0, and then that to 0, that to 0. And then you obtain just this first equation, x1 dot is equal to a11 x1 plus b1 u, and y is equal to c1 x1 plus du. So although you have computed this balanced system, there is information in this matrices A21, A22, A12, B2, C2 that you throw away in balanced truncation. So Guyane reduction or singular perturbation approximation or balanced residualization are ways to bring that information back into the system. And the approach, as I said, is exactly Guyane reduction. You set x2 dot to 0, so then you can solve the lower equation for x2, and because of this consideration that I just gave you on the previous slide, you know that A22 is a stable and thereby invertible matrix. You can do it. And you obtain that reduced order model. And this has the same properties as the balanced truncation model. It's still stable. It's minimal. The same error bound applies. And now it has steady state 0 error, or 0 steady state error, meaning G0 is equal to G hat of 0. So you probably have good approximation also in low frequency range. But now you have D hat is no longer D. And that means for frequencies going to infinity, you don't have convergence of the two models anymore. So you will have some error at infinity. That's often not so problematic with an error at 0, like an error at 0, but it depends on the model that you choose, which is the better thing to have, 0 error at 0 or 0 error at infinity. Good. Yeah, so that I just said that we always have A22 invertible and under the assumptions that we made. And yeah?
Can we use a combination in the sense that for the low frequency we use the Guyane, so we actually construct two transfer functions. One
yeah, that's,
low frequency, one for
you can switch between models, of course, if you like. Yes, but that's then task of the engineer to decide whether he wants to allow himself to switch between two models if you pass a certain frequency. Yeah. Okay, so that I said already, and this should read if the original system is not minimal, then we first have to compute a minimal realization using balanced truncation, and then use here only the minimal part of the realization, or use the minimal realization here. So you have to first eliminate all the uncontrollable and unobservable states before you can do that, because of this assumption here that you have to kick in order to have invertibility of A2. So the same techniques appear over and over again in many areas, and that's true up to nowadays. Also in the research that we do in model reduction nowadays, you will find papers doing the same things in journals on electromagnetics, on fluid dynamics, and biology maybe, and without the communities knowing of each other and knowing that they are doing the same thing. Last but not least, for the last, say, 10-15 minutes, I want to briefly discuss other methods that are based on the same principle of balanced truncation. So the only, if you lean back for a moment, the only information that you need to do this SR procedure Let's just go back to that. It's a while ago. Here's the proof that I gave on the blackboard. I think I can do that faster. So here's this SR procedure to compute the reduced order model. Here's that line that I forgot that it's there. You need a P and a Q that are factored in this way, that can be factored in this way. Nobody tells you that that has to be the reachability and the observability gramian of the system. You can just take any symmetric positive semi-definite matrix here. The question is, will that give you a good reduced order model? Of course. If you use the reachability gramian and the observability gramian, it gives you a nice model with nice features as long as your Hankel singular values decay fast enough. Because of the error bound, you know that if they don't decay, you don't get a good approximation. But maybe there are other P's and Q's around that also give you good approximations. And what I want to show you is that there are actually other P's and Q's. So the classical balanced truncation that we just discussed, that uses the controllability aka reachability gramian of the system and the observability gramian, which solves the dual Lyapunov equation. So the issue that we still have to solve tomorrow is how do we get S and R from the Lyapunov equation, from solving the Lyapunov equations. That's a numerical linear algebra problem that we have to solve. Variant number 1, that uses actually what I was asked in the break, feedback equivalence of linear systems. So in the equivalence class of linear systems, you don't only allow state transformations, but there's also something called feedback. So you allow yourself modifying your system in the way A plus BF X plus BU. So you have a feedback matrix here. And if you use for the feedback here so-called linear quadratic regulator and do the same for the say for the adjoint system, which gives you, if you know control theory, the Kalman filter as the feedback operator. Then apply classical balanced truncation using the observability and the reachability gramian of that system after feedback. Then you can also do model reduction for unstable system, because we know from control theory that feedback using the LQR design, the linear quadratic regulator, stabilizes the system. So that particular F here makes this matrix stable if A was unstable. And the same is then true for the dual equation. And then you can apply classical balanced truncation. And this is, in a way, what is done here in one step. Namely, if you compute that feedback F, you have to solve this algebraic Riccati equation. I can, in LQR, that F is equal to minus B transpose P, where P solves algebraic Riccati equation, the one above. And the same then in the dual situation, you also get that equation. So what people then have suggested is, why not use these P and Q directly to use for this balancing use that here and then apply the SR procedure. And that's basically equivalent to the two-step procedure that I just described. So you, rather than solving Lyapunov equations, you solve this Riccati equation that you would have to solve here anyway. You use that P and Q in your SR method to implement the truncation and get a reduced order model. That I will tell you about the properties of this approach at the end. In any case, it gives you a method to do a balancing type of model reduction for unstable systems. Issues. This is now even worse than the Lyapunov equation. Yeah, it's not. It has the Lyapunov equation as a part. Here's APP plus PA transpose plus B transpose B. But there's here this guy that's nonlinear. It's quadratic. So this equation has a lattice of solutions if you're lucky. It may have a continuum of solutions if you're unlucky. But it has one distinct solution, and that's the one you are after. It only has one solution that is positive semi-definite. All the other solutions are indefinite, or maybe even negative semi-definite. And that one you can identify and you can compute, and I will show you how to do it tomorrow. And that's the good thing. So the solution structure of these Riccati equations is an issue of, or was an issue of research that basically solved in the 80s and 90s of the last century. There's many papers. There's a book on algebraic Riccati equations by Peter Lancaster and Leber Rotman. I think that's given in the references, where you can find all the theory about the solution, possible solutions, and so on. Under the conditions that we assume here, this particular solution, which is positive semi-definite, and it's the only solution that gives you a feedback in that form that stabilizes the system. If you make that additional assumption, then you have a unique solution that you can compute. Okay, then there's balanced stochastic truncation. It's called stochastic because it was first applied in the world of stochastic systems by Desai and Pahl. Green made it amenable for state space computations and showed that again we have to solve two matrix equations. The first is the reachability Lyapunov equation, and the second is a weird algebraic Riccati equation. The derivation of that is far beyond the scope of this course. But it's again, it looks a little bit here. It has a Lyapunov operator like the observability operator. It also has the constant part of the observability Lyapunov equation, but scaled by this matrix in the middle. So D in that case shouldn't be 0. And it has this quadratic term, which here has a different sign than this one, these ones. That's a little bit an issue for some methods in Riccati equations, but you can deal with it. Then there is positive real balance truncation. It's again based on balancing or using two Riccati equations. It's related to what is called in system theory the Kalman-Yakubovich-Popov-Anderson lemma, or Kalman-Yakubovich-Popov lemma, mostly, sometimes with Anderson. And this only applies again to stable problems, but it has nice properties that we will see in a second. And there is a zoo of methods. There's other ones, bounded real balanced truncation, that also uses two Riccati equations for P and Q, solutions of Riccati equations. H infinity balanced truncation aims at robust control design, so the reduced order model can be used to design a robust controller. Again, two Riccati equations give you P and Q. So in all but classical balanced truncation, you will have to deal with Riccati equations if you want to apply these methods. And why are these methods nice? All methods that I showed you preserve stability if your original system is stable. So this is inherent in all methods. Positive real balanced truncation preserves passivity. That's a property that I showed you when we started talking about model reduction. It's important in microelectronics, in circuit simulation, and so on. That's a property you want to preserve. Minimum phase is a property that you may want to preserve if you do control design, because if you have a non-minimum phase controller, that doesn't work in practice. It's not robust. Or if you base your design on a non-minimal phase system. Actually, a phase diagram is the second part of the Bode diagram that we have never used so far. If you look at if you use the MATLAB command Bode instead of writing your own procedure, you will see that you often have a very good, nice approximation of the transfer function. But if you look at the phase diagram of your system, it's way off. Balanced stochastic truncation does a better job there. So it also gives you a nice phase diagram. Bounded real balanced truncation, for instance, gives you, well, a bounded real system is identified by the property that the norm of the transfer function is less than or equal to 1, and that is preserved by bounded real balanced truncation. And you've got computable error bounds for all these methods. That's the classical one that we know, that we just have discussed, of balanced truncation. LQG balanced truncation. This is only true in this form if your original system was stable, I have to admit. Yeah, if in this unstable situation, you have to put that in quotation marks. Because you first have to factor your transfer function into two rational functions which are both stable. And that's always doable. And then that error bound holds for the two factors of that you have obtained. That's getting too tricky. Balanced stochastic truncation has this error bound. It's a relative error bound. It's a method that aims at, when we talked about balanced truncation, we always had this expression, H infinity norm of G minus H infinity norm of, no, other way around. The H infinity norm of G minus G hat in mind. If you directly go for the relative error, then balanced stochastic truncation is a method of choice because it gives you directly a relative error bound. So if you want to have a relative error bound here, you divide by G infinity, you divide the bound by G infinity, but here you get it in that form directly. They all can be combined with singular perturbation approximation. Obviously, you apply the balancing procedure based on the gradients that you have used in the method. And then you get your new system in balanced coordinates, and then you apply the singular perturbation approximation procedure. I don't think, so if you want to have an exercise for a bachelor student, that all the properties have been proved for all the methods combined with singular perturbation approximation. So I know there are papers discussing BST combined with singular perturbation approximation and proof that the error bound is preserved, but that's, I think, not done for all of the methods. And of course, this easy explanation of all these methods, just exchanging the gradients and applying this SR implementation of balanced truncation, can be easily modularized. Yeah, you can have a function that implements the truncation procedure once you've given the gradients. And then you just exchange the way you compute the gradients, and you have an implementation of all the methods on the slide. So that's a nice feature here. You can modularize the computations. I have tried to write a MATLAB toolbox that does that, but that's incomplete work since many years, I have to admit. But you can download this toolbox, which implements some of the methods, at least for using dense algebra, from my webpage. It's called MoreLab. And there's also one semi-professional implementation of some of the methods available in the so-called Slycott model reduction toolbox for MATLAB. Buy it. I'm a shareholder of the company who sells it. No, it's not. We don't have shares. It's a company with 2 people employed, so it's very small. And it doesn't make any profit from the MATLAB toolboxes. And it implements balanced truncation and some of the variants, but not all. In particular, not that one, and not. It doesn't implement positive real and bounded real, and even not LQG balancing. I think it only has balanced truncation and balanced stochastic truncation. Modifications for unstable systems of some of the methods that use a different approach, that use the approach of separating stable from the unstable part. You can always find a transformation so that you can split your transfer function into G minus, which would be the part having only stable poles, plus G plus, which would be the part having all the unstable poles, and then you apply model reduction just to that part. And then you replace that with the approximation, and then you put it back together and get your approximate transfer function. If you only have very few unstable poles, that's still a good reduced order model. But if you have many unstable poles, of course, that doesn't work. But that's implemented, for instance, in that Slycott toolbox for MATLAB. There's also a way to do that in multiplicative fashion. Same idea. So plus or times. To do the splitting with respect to multiplication is more involved. Yeah, and it also has some methods that we have not discussed. But so these are the 2 toolboxes in the MATLAB robust control toolbox. I think you also find an implementation, at least, of balanced stochastic truncation. Okay, that was all I wanted to say for today.